Yeah, my name is Richard Morris. I'm a VP of Business Development at ACI Materials. I spent a lot of my career in this business, and before that I was in materials for printed circuit boards and flexible circuit boards, and I feel like my talk's going to sort of go full circle back to my earlier career of actually being able to build true circuit boards with print electronics. So a little bit about ACI Materials. We're a company based near Santa Barbara, California. We make inks, coatings, and adhesives that are extremely conductive, can be reflow soldered. Some of the materials stretch extremely well. Some of them are used for heaters. Some can be bent many times. Some shield, electrically EMI shield, and some are washable, and some survive re-entry from space. And the key to ACI's manufacturing is in their cavitation, high viscosity cavitation dispersion. And, you know, I've been in the coatings and inks business for a long time, and there are a lot of very traditional ways to manufacture coatings, three-roll milling, bead milling, etc. This is really a new way to disperse metallic and even pigments, carbon nanotubes, graphene very, very efficiently and evenly. If any of you know much about these particles, they often come agglomerated, and to really get the best performance out of them, you need to break up agglomerates and disperse them very, very evenly throughout the coating or the ink, the conductive ink or whatever, to get the best performance. And the way cavitation works, if you've ever seen a propeller on a speedboat, if you spin it too fast, you create vacuum bubbles, which then implode, and they start to erode the impeller. This is the same sort of theory behind cavitation, high viscosity cavitation, is we are forcing materials through and creating these small vacuum bubbles which create these very high energy jets that break agglomerates apart. And it really gives very high performance coatings, especially with metallic silver flakes and other things, as well as carbon nanotubes, as I said, graphene, and certain pigments and other particles that are difficult to disperse and stabilize. It makes a very stable coating, but most importantly, it gives you the best mechanical properties out of a coating, the best conductivity, and also very consistent quality, because we're not losing these. This is fully enclosed the way we manufacture, so it makes very consistent products with very high performance. In the conductive ink space, you have three different conductors. You have the traditional polymer thick film, which are percolation, where particles touch and you get the electrons jumping from particle to particle. But there is some resistance as you have resin in there for your adhesion to your substrate. You've then got nanomaterials, very tiny materials below 1 micron. They pack well, give you very good electrical performance, but you can't put enough resin, adhesion promotion materials in there to get great adhesion. So we work with semi-sinterable conductors. That's mixtures of particle sizes that actually sinter at low temperature to get very high conductivity. Now, really, I've spent a lot of my time not just in materials, but in manufacturing. I was 10 years in roll-to-roll and sheet-fed manufacturing of print electronics. And, you know, there are various production methods, but still predominantly our industry for high, you know, medium, low, and high volume is sheet-fed screen printing. But we're also edging now with these materials into roll-to-roll screen and flexo printing for high definition. But what's most important is not printing at high speed, it's drying and performance at high speed with a wide process window for depositing very thin to very thick. So this is a look, and it's a little bit historical, at our Alchemy Ink series on top, curing at about 135 centigrade against other semi-sintering silver inks, against copper inks that require higher drying temperatures and some compression to get their conductivity. And it's really about getting that cure time down to use tunnel dryers and roll-to-roll dryers that are much shorter. So you really want a dwell time of 1 to 2 minutes. And going higher temperature with our inks, we can get that to that 1 to 2 minutes and very conductive. With this semi-sintering type technology and nanoparticle technology, you're getting to 3 milliohms per square. The one nice thing about semi-sintering technology is you can print at less than 2 microns and above 20 microns with these types of materials. And really then to start looking at flexible electronics, components are small, so you want to be able to print high definition. And by being very conductive, you can get that conductivity close to copper foil, which is what you're trying to do, but also you need to be able to print very fine lines. And we can print thin with stainless steel and V-mesh and other types of very fine screen mesh or flexo print and get down to 100 micron line in space. I mean, narrower, more dense circuitry than that, but I think we're sort of now starting to look at production getting down towards that sort of line in space to get quite small components, starting to get down to 0402s, 0201s and smaller. So that's very important in conductive materials if we want to get to really decent circuit densities with a lot of components. Now, print electronics sort of grows in steps. We've had human machine interface membrane switches for 30, 40 years before I got into this business. And then there's been heaters. This is a heated skiing goggle, transparent with our ink on the bus bars from Bopler and Chasm Materials. So they're heaters, human machine interface, sensors. This is Flexu, sensor, temperature, pressure sensor to monitor lithium ion battery packs, and low power displays from Invisible. But really, one of the things that needs to be is connection to standard components. And print electronics up until now has been all conductive adhesive attach. So with our semi-sintering materials, we can low temperature solder, and this has a lot of benefits. You know, the components are going to self-align. You can start using tin finish components as well as standard gold LEDs, for instance. We don't need potting compounds over the top to have good solder adhesion, get to smaller components, lower resistance, better thermal. So really being able to reflow, we're now getting in the mainstream of electronics assembly. And this is a slide that really shows that even the best silver-filled epoxies, they do start to rise in resistance on the joints. You start to get some corrosion with tin, for instance, whereas solder, you get very stable connections with tin finished components. And we've done quite a long study on various finishes of polyester, TCA, that sort of acid etched matte polyester, ST505, 506, really almost bare polyester, and even Kapton, and looking at component shear with some various alchemy inks. You're going to break your nail trying to get these components, 06, 03s off there. So very secure bonds to the surface. We have worked closely with Volterra. They build a very nice prototyping piece of equipment where they can take production-ready materials and dispense them for prototyping, use those same materials in production. And this is showing a really nice, what they did is a roulette board. It's like a 1.5 layer, so it's got jumpers in there. And then they're placing, placing components on the solder. Even hand soldering to that polyester circuit at about 160 centigrade. And they do put Glock top on top just to secure those larger components, etc. Get a nice circuit. So this is prototyping. We want to go a lot more dense in production. And really there's a lot of discussion about whether silver or copper inks are best, are going to be lowest cost. And really, you know, initially when you look at this, sintered copper is a lot cheaper, almost half the price of a silver circuit. But when that copper oxidizes, it's not, it's porous. It actually ends up being less conductive, and pretty much on a par on price to a much more expensive ink, but at the same 15 milliohms per square, you've got pretty much the same cost building one with a copper nanomaterial versus our Alchemy silver ink. You know, I want to talk a little bit about sustainability. Fully additive circuits are, of course, using a lot less water, less energy, etc. So they are intrinsically more environmentally friendly. People are building copper antennas and things on paper, but one of the issues with copper on paper is when you leach it in acid rain or whatever, you will get heavy metals in the water. So there are issues around copper on paper. The one nice thing about polyester-based circuits is people are now starting to downcycle. Eastman Chemical and others are starting to take in polyester film, wash off the inks, and those can be recycled. But in reality, the main area of recycling I see driving forward is on rigid circuit boards with Jiva board and others, making more environmentally friendly rigid boards because they're much higher volume. Eventually, we may start seeing some recycling of silver on boards. So that will come, but I think the drive is on rigid boards first, but fully additive, definitely more sustainable. So that's really wrapping up our view of where things are going to fully additive, traditionally soldered boards, driving that way to much higher density. ACI also has stretchable inks to make functional textiles, heaters, sensors, other type things if you come to our booth out there. And we make full material stacks. We don't just make the conductive ink, we make the insulators, we make the heater inks, we even make a low profile connector and have a substrate that works very well. And so we build these stacks of stretchable materials, and really that is progressing. That's come a long way in the last 3 to 5 years on that side of things. And this is just another demonstrator we did with Covestro or with their Sensortronics and TapeCon and ACI, a shoe sensor with pressure. It's showing the gate in there just to show an application. I'll run this video. So you can see that's the sensor in the shoe. The buttons are lighting up where you've got the pressure. So this is one application in smart textiles. And smart textiles, you know, where are the significant applications? What we're seeing right now is sensors and heaters, most typically, automotive sensors in the doors, in the center panel, on the seat, using touch, medical heaters to help healing, heated braces, that type of thing. I do think smart clothing will follow. You know, you've got wire wound heated gloves. These are bulky, those wires can break, they're cheap, but I do think the low profile nature of print electronics and stretchable, when they're designed right, is going to make some really nice heated gloves, very low profile heated gloves and heated socks. We're also looking at connecting. It's not easy to connect to these materials. It's easy to tear and that type of thing. So we've working with a partner, another partner in our industry, Duratech. A D-bit is this heat applied connector, very low profile. We're starting to get into testing. We've done testing internally for washing. We're really getting into production, looking at how many washing passes it takes, how durable that is, very easily put on, very low profile, because typically to try and connect to stretchables, people are using snaps or traditional electronic connectors. These are bulky. You want something slimline. And then we're also looking at materials and cost reduction. You know, polyester film is a very low cost film. TPU is a little more expensive. There are many steps to transferring TPU, but we're working closely with Covestro in this space. Just on the, you're seeing actually a heater being stretched back and forth and staying, you know, pretty much the consistent temperature the way it's designed. And and also simplifying the build, working on simpler steps to put the electronics onto the fabric and lower the cost of that build. That's the big driver to get to smart clothing. And I think my 15 minutes is up. So thank you very much. And thank you, TechBlick. Thank you for staying awake.
Thank you, Richard. So any questions?
Sure.
You mentioned this connector. Can you say or something about the height? And
Yeah, I don't know the exact height. It's probably about, it's less than a millimeter. It's probably about a 0.5 millimeter right now. I could give you the exact height. I don't know it off the top of my head. It's a stack. That stack has breathability because it's just through pressure and heat on there. It's got a vent in there and some other nice things it's got built in. We're looking at ways to build it even simpler than that. But yeah, it's probably right now 300 microns thick, maybe 300 to 500 microns thick, something in that region. There's just one outside, an early stage one. We're just getting out some early prototypes to some customers to do some testing. That's really not just us saying this. We want them to really test it, and then Duratech is also sort of getting all their tooling together to build it in high volume. So we're still at that early stage, but I would think it would be, if all goes well, it will be released sort of towards the end of third quarter, something like that, fourth quarter.
Any further questions? Did you have any washability data?
Right now, it's about 20 washes. We're going to do a lot more washing with it going forward. Yeah,
Okay.
yeah, and salt water and that type of thing. That we've done some of that internally. We also want our partners to do that as well. But we think fundamentally, it's a pretty good design.